Welcome back. This is video lecture 25.1. We are starting chapter 25, which is all about a property known as capacitance. And we'll start with section 1, chapter 25, which introduces this concept and defines it, the concept of capacitance. So let's just start with a key idea, meaning a basic description of what a device called a capacitor is. Okay, so we're talking in this chapter about a device called a capacitor, and one of its properties, the one we're going to focus on, is called capacitance. And I do put those intentional emphases on the two words to try to make clear. There's the actual physical object, capacitor, and it has a property called capacitance. So what is a capacitor? A capacitor in terms of electrostatics? Well, it's really any device that separates positive and negative charge. Puts positive charge in one place, negative charge on another. Turns out that in doing that, it stores what we call electrical energy, which can then be used later to do work. Now, very generally, you will discover that capacitors consist of two electrical conductors separated by an electrical insulator. That separation is very important. The two conductors cannot be in any kind of true physical contact, because if they are, they'll quickly share the plus and minus charge excesses and pretty much neutralize all that out. And you'll no longer have a charged up capacitor, and a capacitor that's not charged up is of no use. So you must have two electrical conductors separated by an electrical insulator. And here's a drawing of a very generic capacitor. Not the kind we're actually going to study, but just a general one. Okay? The two conductors are there drawn in kind of a gold or orange color. One of them has an excess charge, of plus Q, and the other has an equal but opposite amount of excess charge, negative Q. And when you have a device called a capacitor, the two conductors that are charged like this are called the plates of the capacitor. Okay. So there they are, plus Q and minus Q. Each one is a conductor. Notice, because of the charge, you get electric field in all of the space around the two conductors, and you can see some electric field lines to basically show you where the electric field is strong, where those field lines are bunched together, and what direction they point in, away from the positive charge and towards the negative charge. All right, that's a very general description of a capacitor. Let's start focusing on the shapes of capacitors we're going to be dealing with. And by far, the most common shape we're going to deal with in this chapter is called a parallel plate capacitor, because the two conductors that are the plates in the capacitor are flat conducting sheets or planes that are layered parallel to each other. And depending upon how far you've gotten in the most latest experiment in lab, which is all about capacitance, you may have started making your own parallel plate capacitor. Right? You use these two thin aluminum sheets, and you just imagine them being stacked parallel to each other. But they can't be touching, not like that. There's going to have to be something in between them. Okay? You could put a piece of paper or two in between them, because paper is an electrical insulator. Okay? Then you have a sandwich, so to speak, with the two conducting plates and the insulating material between them. So this is an example of a parallel plate capacitor. You're going to make one. So you can see there's an upper plate and a lower plate. They each have the same overall surface area, A, and they're separated by a distance, D. And what we're going to do is we're going to build up positive charge, plus Q, on the bottom side of the top plate, and an equal but opposite amount of charge, negative Q, on the top side of the bottom plate. And that will produce electric field in the region between the plates. That will produce a potential difference between the plates. Here on the right, we have the same structure, but in a side view, where the plates look like lines. The top plate has charge plus Q on its bottom side, and the bottom plate has charge minus Q on its top side, the sides that are facing each other. And we get a nice, strong electric field in the region between the plates, and that's represented by the blue arrows, and it's quite uniform in the region between the plates. We get some pretty complicated stuff going on around the edges of the plates. You can see the electric field lines are more curved there. And that's realistic, that does happen, but we don't want to have to deal with that. Okay? So one of the things we're going to do is we're going to approximate that electric field between those two parallel plates more like this. Top plate, bottom plate. Just make a nice uniform electric field that points away from the positively charged plate and towards the negatively charged plate, and is confined to the region just between the plates. I'm waiting for my program to catch up with my writing here. Okay, hold on. Okay, I'm back. And there you can see that I've drawn the two plates over on the side, and I've just drawn nice uniform electric field lines pointing away from the positively charged plate and towards the negatively charged plate, and we ignore all that complicated stuff on the edges. That's how we're going to think about the electric field between these plates. That's a pretty good approximation, especially when the distance between the plates, little d, is small compared to the two dimensions, the length and the width of the plates, which is what the drawing there implies. Okay? All right, now, so what do you do when you have a parallel plate capacitor? When you put it into an electric circuit, how do you use it? I'm going to talk about that now. The whole point is, by using some kind of source of energy, like a battery or a power supply, or a function generator, you are going to what's said to be charge up the capacitor. And of course that means what I've been talking about. Put positive charge on one side of one plate and an equal but opposite amount of negative charge on the facing side of the other plate. So the picture here on the left, we're going to talk about charging the capacitor. The picture here on the left is a rough schematic of exactly what a circuit would look like on a tabletop. You have a battery with a plus and a minus terminal, which really means high potential and low potential terminals. And we've taken conducting wires, and we've connected with a wire the high terminal of the battery to one of the plates of the capacitor. We're going to label that plate H. Now we've taken a wire and we've gone from the low terminal, L, of the battery into just a mechanical switch, and then to the other plate of the capacitor, plate L. And then when we close the switch, we'll end up charging the capacitor. Okay? Now over on the right, so that's a schematic representation of the charging circuit. That's roughly like what you could have on a tabletop in a lab. Now on the right is what you'll see in books, and you'll draw yourself on paper. It's called a circuit diagram. You'll see it in the lab manual. It represents the electric circuit way of talking about, denoting the actual circuit on the left. All right, now, this shape here represents the battery. And it's got a short line and a long line. And the longer line is the high potential side, and the shorter line is the low potential sides. They're labeled plus minus. And then it represents the actual terminals of the battery, there and there. And the battery's job is to produce a certain potential difference across its two terminals. And that's what this V here represents. The potential difference across the two terminals of the battery, produced by the internal chemistry of the battery itself. So to those terminals we use wires, and with one wire we hook up to one plate of the capacitor, and since that wire is connected to the high terminal of the battery, the high potential terminal. That'll be the high potential plate of the capacitor. And then we go through a switch with another wire to the other plate of the capacitor, and that'll be the low potential plate. And then all you got to do is mechanically close that switch, and you will have a complete circuit, and the battery will do work, and will end up charging up the capacitor C with plus Q building up on the right face of the H conductor, and an equal and opposite amount negative Q on the left face of the L conductor. And that will continue until the potential difference across the capacitor equals the potential difference produced by the battery, V. And then we say the capacitor is fully charged. Now, this was learned originally by experiments, a lot of them in the 1800s, and one of the persons doing those experiments was Michael Faraday. And so these experiments that were done, here's what they show. The magnitude of the charge on either conductor, magnitude, we're just going to call that Q, right? Because one is plus Q and the other is minus Q. So we just call the magnitude of the charge Q, is directly proportional to the potential difference V between the conductors, which is determined by the potential difference V of the battery. So in other words, you charge up your capacitor with a particular battery, producing a potential difference V, you get a certain amount of charge Q. Swap out that battery for one twice as strong that produces twice as big a potential difference, 2V. The total charge on magnitude on either plate will be 2Q. Okay? So the charge magnitude that's induced on either conductor is proportional to the potential difference supplied by the battery and therefore across the capacitor. So all you have to do is introduce a proportionality constant, and that's the symbol capital C. And then you've got a nice little simple formula between the magnitude of the charge on either conductor, the potential difference across the conductor that you could measure with a voltmeter, and this proportionality constant denoted by capital C. I should mention, by the way, that the convention in this chapter is to use the symbol V, italic V, for the potential difference across the two plates of the capacitor. Chapter 24, we would have denoted it delta V. It's a potential difference between the two conductors. But in this chapter, everybody just calls that potential difference V. Now, that proportionality constant denoted by the symbol capital C, that is a property of the capacitor called its capacitance. Okay? C is the property called capacitance. You can think of capacitance as a measure of a capacitor's ability or capacity to separate charge. A bigger capacitance means you'll get a bigger charge separation for a given potential difference. Since we have a new quantity here, we should talk about its unit in the SI system. The SI unit of capacitance, well, if Q equals CV, then C equals Q divided by V. So the unit of C must be the unit of charge, Q, divided by the unit of V, potential difference. That's 1 Coulomb over volt. Coulomb per volt. Now that combination of Coulomb over volt is given its own name and symbol. Capital F for Farad, after Michael Faraday. An important thing to know about capacitance of any capacitor, that property, capacitance, capital C, it's really just a geometric quantity. It depends on the size, shape, and separation of the two conductors. And even though C is related to Q and V by the equation I marked with the star, here's a very important point to note. The capacitance of a capacitor is not determined by the Q or the V. The capacitance of the capacitor is determined by size, shape, and separation of the two conductors. Now, the SI unit of capacitance is the farad, but a capacitor with a capacitance of 1 farad, up until not too long ago, would have been unheard of. 1 farad would be thought of as a huge amount of capacitance. What's more common in garden variety capacitors that would be used in electric circuits is to have capacitances of microfarad, 10 to the minus 6 farads, or nanofarads, 10 to the minus 9 farads. However, for reasons we'll learn later in the chapter, it's now, and with some breakthroughs in an area called material science, it's now possible to make a capacitor with a capacitance as large as 1 farad. I'll show you one in the actual class. All right, so now what I want to talk about I want to go on now to chapter 25, section 2, which is now going to help us calculate the capacitance for a given capacitor once we specify its size and shape and the separation of the two conductors. Okay? Let's start with the parallel plate capacitor. I'm going to walk you through how we calculate get the formula for its capacitance. So we have a side view down here below of the two conductors on the parallel plates. They're shaded there in gray in the picture, and they would represent you looking on the edge on from these two plates like this. But they've been drawn with some sizable thickness. That's okay. So there's the upper plate, if you like, H, and the lower plate, L. The upper plate has been given a total charge plus Q on its bottom surface. That's where it's going to show up. And the lower plate has been given an equal but opposite charge negative Q on its top surface. And those are going to produce, those two charge distributions, nice uniform electric field away from the positively charged plate and towards the negatively charged plate. And that's what these electric field lines are showing. We want to get a formula for that electric field. Note the plates are separated by a distance d, and although it's hard to see here, each plate has an area A. What would that be in this case? It'd be this surface area right here of this rectangular region. Okay? Of course, you're looking at it here edge on. So it's this surface area here or here. That's the A. Okay? All right, so we've got a charge Q on the plates. What that really means when we say that is plus Q on one plate and minus Q on the other. Now we're going to calculate the electric field E between the plates using Gauss's law. We've actually already done this in chapter 23. Found the electric field between two oppositely charged parallel conducting plates. But I'm going to go through this calculation again because I think it's good practice. So, since we've got a nice uniform electric field in the region between the plates, we're going to pick a Gaussian surface that's shaped basically like a rectangular box. Now we're going to see it here in an edge view, but I'm going to draw it in red. Okay? Part of it goes through the upper conducting plate, extends around the edges, and then the rest of it goes through that middle region. This is an edge view of our Gaussian box. And we need to write down an expression for phi electric. We need to calculate the electric flux from electric field vectors piercing the surface of this Gaussian box. So we have to be able to visualize where the piercing is. Do you see where it is? It's right here, where we have electric field vectors piercing through this lower area right here on the Gaussian box. And the electric field vector is piercing downward, and the dAs on that part of the surface would be downward. So the E and the dA are in the same direction, and the E is uniform. And so this flux integral is just going to reduce to the magnitude of the field times the area A, because that's the area that's pierced by electric field. Okay? So that's what the flux formula looks like in this situation. Now the other thing I need to keep track of for Gauss's law is the enclosed charge, Q enclosed. Do you see where it is inside the red Gaussian box? it's smeared out uniformly over that bottom face of the top conductor. I just shaded it there. And it's the total Q for that top conductor. It's all inside the Gaussian box. Okay? Because the Gaussian box, it's hard to denote, right? But it's got a surface along here, and it goes this way, and then the top of it lies inside the metal. The metal's very thin, but you can still have that. So the point is the Q enclosed for the Gaussian box is the whole plus Q on the top plate. Now use Gauss's law. Electric flux equals Q enclosed over epsilon 0. Magnitude E times the area equals plus Q over epsilon 0. Solve for E. Q over A epsilon 0. And it's uniform in the region between the plates. That's really handy. That's one of the reasons the parallel plate capacitor is our favorite one for teaching. Now, one thing you might recall, depends if you recall what we did in chapter 23, but you could take, I'll write it over here to the side, the total charge on the upper plate divided by the area of the upper plate and call that the charge per unit area, sigma, on the upper plate, the surface charge density on the upper plate. Then the formula for the electric field magnitude is just sigma over epsilon 0. Right? That's the same way of expressing that. Okay? And that's the way, that second way, is how we wrote it in chapter 23. All right, now there's another step. We're going to integrate the electric field along a path to get the potential difference V. And we're going to do that by integrating from an initial point I on the bottom plate to a final point F on the top plate, going in a straight line upward from I to F. Yeah, I'm going against the electric field, but that way the delta V I'm going to get will be positive. So now I use V final minus V initial equals, let me get rid of this so I have room to write, negative integral from initial point to final point of E dot ds. All right, so V final minus V initial equals negative integral. Okay, there's my path over there, that green line. It goes straight up. Okay, it's caught up with me. So my ds is up, but my E is down. So when I do this dot product, to be technically correct, I need magnitude E, magnitude ds, times cosine of 180 degrees. Okay, we've got the problem again. Okay, hopefully this will work. So magnitude E, magnitude ds, cosine of 180 degrees. Remember, the cosine of 180 degrees is negative 1. Okay, this isn't working very well, folks. So I have two negative signs multiplied together, which gives me a positive. And now we just call V final minus V initial the potential difference, V. So V now equals integral of E, magnitude ds. But E, magnitude, is uniform. You get to bring it out front. Then you just have the integral of all the little ds's, little steps, from point I to point F. Well, that'll just be the total distance from point I to point F, which is d. So this is just magnitude of E times the distance d between the plates. So now we have a nice simple formula for the magnitude of the electric field V and the distance d between the plates. Okay? All right, now we're going to combine that expression with the defining formula for capacitance, which is that formula, Q equals CV. That's the defining formula for capacitance. All right, so for the Q, what I'm going to do is I'm going to go up to the E formula. Let me bring it back into view. See it up there for the electric field? Q equals E times A times epsilon 0. So I'm going to write that for the Q. I think we can just fit that in here. Equals C, and then for the V, magnitude E times D. Okay, now the E magnitudes cancel, and I just solve for C. I get epsilon 0 times the area of the plates divided by the distance between them. Get that back into view. And so here you see that now, that result written over here to the side. Now that's the capacitance formula for a parallel plate capacitor. Specific shape. 2 flat parallel plates. Each has an area A, and they're separated by a distance D. Notice it just depends on geometry. Okay? Note also, though, one key property of capacitance that follows right from this formula. The closer I put the plates, that makes D smaller, right? But D's downstairs. That makes C larger. So the closer the plates, the larger the capacitance. Now there's some dangers in putting the plates too close that we'll learn about later. Okay? But in general, the closer the two conducting plates, the larger the capacitance of the capacitor. Now there can be other shapes for capacitors. And different shapes have different capacitances. And we will talk mostly about the parallel plate capacitor, but I want you to at least be aware of two others: the cylindrical capacitor and the spherical capacitor. The cylindrical capacitor is actually pretty common too. Now the picture here is going to be a little bit confusing, so I'm going to draw my own version of it. Right? First, I'm talking now about the cylindrical capacitor. And I'm going to draw a side view over here as best I can. And the cylindrical capacitor is actually like a coaxial cable, which is one of the geometries you did in experiment 10. You have an inner conducting cylinder of some length L this way, conducting, and you surround it with a conducting cylindrical shell, which I'll try to represent like that. Okay? And the inner, and here's the central axis going down the middle. The radius of the inner cylinder is denoted A. Let's make sure the program can catch up with me. There it is. I'm losing my patience here. Okay, I'm trying again. So the radius of the inner cylinder is A, and in essence the inner radius of the outer cylindrical shell is B. And my figure is actually, and so is the book's figure, misleading. Because what we really mean is that the capacitor's L is much larger than the A and the B. So it's much longer than it is wide. Okay? But we always draw it that way because it's too cumbersome to draw it really long. Now, this view over here is, if you like, an end view. If you took the cylinder, the cylindrical capacitor, and you tipped it and looked at it end on, then you'd see the solid inner conductor of radius A, and then the conducting shell around it. Okay. And now you want to calculate the capacitance. I'm just going to talk you through this one. So we assume there's plus charge on the surface of the inner cylinder, plus Q, and negative charge on the surface of the shell that's facing the inner part, so that we get a nice radial electric field with electric field lines radiating outward from the inner conductor to the outer one, like this. Nice and uniform. I'll draw some of them. And we use Gauss's law to get a formula for the electric field in that inner region. And I'm going to just write down what that formula is. But I'm waiting for the program to catch up. Okay, I'm just going to write down what that formula is that you get from Gauss's law for the magnitude of the electric field in the region between those two cylinders. It is Q, think of that as the positive charge on the inner cylinder, over 2 pi epsilon 0 L, the length this way, little r. And little r is the distance out to where the Gaussian surface is, which is shaped like a cylinder. Seen edge on, it's like that. R is its radius. Over here, it would look like this. It's got a radius r and a length L. Okay? That's what the electric field's like. That's a chapter 23 problem using Gauss's law for cylindrical symmetry. Then you use delta V equals negative integral from initial point to final point of E dot ds and integrate that electric field to get a formula for the potential difference. And the path they use starts at a point on the outer, like there, I, ends at a point on the inner, F, and goes in a straight radial line against the electric field. And the formula you get for the potential difference, and I might as well take out the delta, because that's what everybody does in this chapter, it is Q over 2 pi epsilon 0 L. And because of that 1 over r, when you integrate, you're basically integrating dr over r, you end up with, interestingly enough, a natural logarithm of the outer radius b over the inner radius a. And then you use q equals cv. I mean, there's the q, and there's the v, and you rearrange it and you can solve for c, and here's the formula over here that you get for the capacitance of a cylindrical capacitor. So if that's what we've got, you can go straight to that formula and use it. And it does depend on size, shape, and separation. See, it depends on the length L this way, on the radii A and B. And the closer those two radii are to being equal, the larger the capacitance. And that's because of that log of B over A in the denominator. So that's the formula for the capacitance if what you have is called a cylindrical capacitor. That's going to happen if you have what's called coaxial cable. Now, the last case is not going to be that common, except in textbooks. But it's a nice handy geometry and it's easy to do. It's called the spherical capacitor. And then what you've got is, well, you just take away this picture. But you can use this same view here because it looks like also a sphere inside a spherical shell. And the inner sphere has radius A, and the outer spherical shell has radius B. You put plus Q on the surface of the inner sphere, and minus Q on the inner surface of the shell, and you get that radial electric field in between. You can use Gauss's law to get a formula for it. Then you can integrate E dot ds from one conductor to the other and get the potential difference. And then you can use Q equals CV, and you can solve for C. And I'm just going to tell you the result for a spherical capacitor. It's right here. 4 pi epsilon 0 A times B over B minus A. So that's if what you have is a spherical capacitor. And again, if the two conductors get close together, the capacitor gets bigger. And that's because of the B minus A in the denominator. Okay, so we'll be talking about capacitance in the class on Monday. So let me just leave you today with a class engagement exercise on Blackboard. And it goes like this. Consider a given parallel plate capacitor with fixed plate size, that would be area A, and separation, that would fix the distance D between the two conductors. Here's the question. What happens to the capacitance of this capacitor when A, the charge Q on its plates is doubled? What happens to C? And then B, the potential difference V between its plates is tripled. That's two separate cases. First, we double the charge Q. What happens to C? Then return to the initial situation and triple the potential difference V. Again, what happens to C? So you answer those two questions on Blackboard for Monday's class. And that's all for this video.